We were discussing Lewis theory through Lewis symbols, and I want to say that not only can Lewis theory address the single bonds, it can also address why a certain atom would want to indulge in multiple bonding, for instance. So, oxygen, if it bonds to only one other atom, it would want to go through a double bond. And you can see that because oxygen has 6 electrons around it, and carbon has 4 electrons of its own. So, in order to, let's just write that carbon has 4 electrons around it, and you have 2 hydrogens, so they're going to bring in with them one single electron. Oxygen, I said, has 6 electrons of its own, so you can put them like this. And if you do so, then carbon is going to have 4 of its own. It is going to have one from this hydrogen, so that makes a total of 6, and then it's going to get 1 electron from the oxygen, and that makes it only 7. In order to get a complete octet, what you would want to do is you would want to bring in this electron as well as this guy in the middle, so that they are together in a double bond. And so your Lewis structure would look like this. Now realize that when you're thinking about the Lewis structure, there's 2 ways really to get to the Lewis structure. One, the way I explained the formaldehyde molecule, is the valence electron method. So basically, all you need to know is the number of valence electrons, and you can get that directly from the group number. On the other hand, you could use the electron accounting method in terms of how many complete octets you need and how many you have through the number of valence electrons that will be involved in the structure, and you can take it from there. For instance, let's say your molecule was CCl4. Then you can say that you need a complete octet for 1 carbon. You need complete octets for 4 chlorines. That means we need total 5 times 8, 40 electrons is what we need. And we have 4 electrons for carbon, and we have 4 times 7, which will be 28. So we have 32 electrons already. And now we go need minus have, and that will be 40 minus 32, so that's 8 electrons. And since 2 electrons make a bond, so this divided by 2 will give you 4 bonds. And that tells you that the central atom, carbon, will have 4 bonds around it. So those are your 4 electrons. And then you place the 7 electrons on chlorine, and that's your Lewis structure. So take the time to go over the general chemistry 1 video. I pulled that for you guys, so you can use that. But if you're comfortable drawing structures, and really you just need to know one of the 2 methods, as long as you can draw the correct Lewis structure, you'll be fine. Okay, so let's try to apply that to some of the molecules over here. The solutions to these are available on Blackboard also, but I'll just go over those real quick. Nitrogen has 5 electrons. I personally like valence electron method a little bit better. Just personal choice. Hydrogen, each of the hydrogens is going to bring 1 electron. And so if you place them like this is your Lewis structure. So now nitrogen has 5 plus 3, 8 electrons, and each of the hydrogens has a complete duet as well. Likewise, if you consider CH3CH2F, that means carbon is bonded to 3 other hydrogens. and then it's connected to another carbon, which is bonded to, I'm just using crisscross. You can use two dots if you like to. You can use cross and a dot to signify that they are different. You can use two different colored pens, you know, whatever works to signify that. So here's a bond, here's a bond, this is a bond, this is a bond. That gives you a complete octet for this carbon. Likewise, you will get a complete octet for the second carbon as well, and for the fluorine atom. So that will be CH3, CH2F. Let's try to get CH3O, CH3. So we have a carbon, and it's going to be connected to three different hydrogen atoms, and the fourth electron of carbon is going to be connected to oxygen, which has 6 electrons with it. And then we have the other carbon atom, which has 4 electrons of its own, and 3 of those are going to go to hydrogen. So again, you know, I showed this way to kind of show that you can color code it as well. So hopefully you can see each of the carbon atoms had 4 electrons of its own and is sharing the rest of the electrons. So complete octet here, complete octet here. And oxygen is making 2 bonds, and it had 6 electrons, so that's a complete octet for oxygen as well. So that will be the structure for CH3O, CH3 dimethyl ether. And next we have BF3. That's the next one. So slide BF3. Boron is going to be our central atom, because as per the rules, the least electronegative elements, or more, is an element in the central part of the periodic table that has a greater tendency to behave as a central atom, and more electronegative elements, or things like hydrogen, which have only 1 electron to offer, these are the ones that will take the periphery. Recall that rule from Gen Chem 1. Boron itself has 3 electrons, complete octet, complete octet, complete octet. Notice around boron you have only 6 electrons, and there's nothing really that you can do about this fact. Boron does form electron deficient compounds because it has only 3 electrons around it. You have only total 6 electrons that are possible, and because of this electron deficiency, boron compounds also tend to behave as what are called as Lewis acids. That means they are great electron acceptors. Now my last compound is C3H4, and really you should take the time to draw this out. There are 2 possibilities over here. C3, so I'm going to arrange the 3 carbons first. Each of them have 4 electrons. And if you try to place the hydrogen atoms around them, there are 2 ways to do that. Let's say we put 2 hydrogens at the periphery, because that's the rule. That's what you want to go with. That's a complete duet here. That's a complete duet here. Let's say I put the other 2 hydrogen atoms also at the periphery. That would mean that the carbon over here and over here, they will have 4 electrons of their own. They will get 2 more from the hydrogen, so that's 6, and 1 from this carbon. That means they will have to pitch in this electron density, and this carbon will have to pitch in electron density, so that it forms a bond to complete the octet. Likewise, you will form 1 single bond, and then another one will be formed by bringing these 2 electrons together. So your structure will look like C, double bond C, double bond C, and an H2 over here, and an H2 over here. This kind of a structure where one carbon forms a double bond on each side and it is double bonded to carbon is what is called as alene. And for more details, grad school first semester. Another Lewis structure that you can draw for this kind of a compound is, again, you arrange these in an array. And what if three hydrogens are together on one side and it's forming a triple bond? That too is a possibility. So take the time to go through some of the Lewis structures. Of course, the problem set asks you to go over some as well. And hopefully that will seal the deal for you in case you did not have a detailed experience on Lewis theory in General Chemistry 1, or you don't remember much from then. Okay, let's talk about formal charge. Now, if you are a formula person, you can determine formal charge putting in the formula that the number of valence electrons as a free atom. From that, if I subtract the number of valence electrons in the bonded structure, that will give me the formal charge. So for instance, if I wanted to put in the formal charge for, let's say, carbon over here, I would say that carbon has 4 electrons on a usual day when you think about carbon as an atom. And in this particular situation, it is forming 4 bonds. So it has actually 4 electrons of its own. So 4 minus 4 is going to be 0. So carbon, when it forms 4 bonds, is going to have a 0 charge. You might have seen the same definition as valence electrons minus half the number of bonded electrons plus all non-bonded electrons, and it basically means the same thing. But that's another formula that one can use for the formal charge. But a quick way that one should realize, that one should note for yourself, because if you're a PCAT MCAT student and you are trying to figure this out in the exam, you have a total of 40 seconds to go over the question and determine the answer. So you should know the valency of each of these atoms at the back of your hand. That means carbon wants to make 4 bonds. Oxygen wants to make 2 bonds. These are things that should come to you like naturally. They should just flow to you. So if oxygen wants to form 2 bonds, and it is doing so in this case, notice the other oxygen. So I'm going to just label that as oxygen 1 and oxygen 2. So if oxygen 1 is forming 2 bonds, oxygen 2 is forming only one single bond, what happens to that other valency of oxygen? It basically is hanging around. That means we are not utilizing the valency of oxygen completely, and whenever you are able to underutilize valency, it will leave a negative charge. And if you overutilize a valency, a valence electron, that will give it a positive charge. That means this negative charge that you're seeing on the acetate unit is basically because the valency of the oxygen is being underutilized, and that's where that negative charge is going to be. So all of the rest of the atoms, for instance, the 2 hydrogens, the carbon, the other carbon and oxygen, these are all going to be completely saturated with terms of their valency, but oxygen is the one which is underutilized, and hence that's where the negative charge would be. You can try another one. How about nitrogen forming 4 bonds? And here you have a positive charge on nitrogen, and so that means that that positive charge should be on the nitrogen atom, because on a usual day nitrogen forms 3 bonds, and right now it's forming 4. That means we are overutilizing the valency. That is the reason that you have the positive charge. And that's an example that I'm giving you here as well. We have an ionic bond which is present between this methyl ammonium unit with the chloride. Notice all of the bonds that are on carbon essentially are saturated. They are forming the number of bonds as they should, as is appropriate as per the valency of carbon. Nitrogen, however, is making 4 bonds and it's allowed only 3. That means this positive charge is going to be on the nitrogen atom. Now, one thing that I would like to say, whenever you would be drawing structures for any of your organic or biochemistry courses, which has a metal, you can never show a covalent bond. Notice in this case it was drawn almost like as if oxygen and sodium basically share electrons. A metal would never share electrons, it would always lose electron, and sodium is probably one of those that loses that electron the easiest. So sodium would lose that electron, oxygen would pick up that electron, and this is how you would write the structure rather than putting in a covalent bond for any time you have a metal in the system. Okay, let's see if we can go over some of these structures. So you have to draw the Lewis structure for these compounds and ions, and you also have to show the formal charges. So you have carbon. Carbon has 4 electrons. Notice, but there is a positive charge. That means that each of the hydrogens would bring with it 1 electron. So you would have that. And we are saying that this 1 electron has been removed, which is why there is a positive charge. So you would say that the Lewis structure would look like you have CH3 and a positive charge is present. So since carbon has only 3 bonds, we are going to say that this carbocation is going to hold a positive charge. Likewise, if you consider the carbanion, in that case, you have the 3 CH bonds, but the 4th position has been given an additional electron, and hence you will have a negative charge due to the presence of the additional electron. So realize that carbon on its own would have 4 electrons, and if that electron stays there, that will be a very, very reactive species. It will be called a radical, and it would be reactive because it wants to give off this electron or it wants to gain another electron, one or the other. On the other hand, if you add an electron, so that additional electron brings in 1 negative charge. If you remove that electron, then you give it a positive charge. So choice A is a carbocation, choice B is a carbanion. Hopefully you can see that NH4Cl is NH4 plus and Cl minus. That's ammonium chloride from your Gen Chem 1 and Introductory to Chemistry days. And that would mean that you have ammonium with a positive and Cl negative is just the counter ion. So ammonium has, nitrogen has 5 electrons around it. Each hydrogen is going to bring in 1 electron with it, and these 2 electrons are going to be given off to that hydrogen in a dative manner, so that the positive charge is going to be on nitrogen. So you draw this as nitrogen, positive charge on nitrogen, and then Cl negative is the counter ion. Okay, I really want you to draw the hydronium ion. So oxygen has 6 electrons around it. Each hydrogen again brings in one, and the third hydrogen is a proton. So both of these electrons are given to that hydrogen. So oxygen is the one that will have the positive charge now. So that's how you would show that. You may or may not show that as an arrow, but realize that that is the coordinate bond that you learned about in general chemistry too, where water is going to react with a proton and give you hydronium ion. All right, the last one is CH3NH2Cl. Let's put that one as well, CH3NH2Cl. So that's a version of NH4Cl. It's just that two of the hydrogens have been replaced by methyl groups. So we are going to have a positive here, a negative here, because you know Cl is forming only one bond. That means the other one is kind of hanging around, so that's why you have a negative charge. And if you have a negative charge, there has to be a positive charge on something. And in this case, since it's nitrogen that's making 4 bonds, that's the one that you're going to say is what is going to have a positive charge. Each of the carbons has 4 electrons of its own, so when you write CH3, it's going to get 3 other additional electrons from the hydrogen atoms, and 1 electron is being shared with the nitrogen, so the octet is complete on both of these carbon atoms. Likewise, when you consider the nitrogen in the middle, you have 5 electrons that are coming from nitrogen, and it's sharing 2 from the carbon and 1 from the hydrogen, and one of the bonds is really, if I wanted to show all nitrogen atoms, and maybe red. So those are my 5 electrons. One of them is going to come through a reaction with the proton, so that you have the positive charge on nitrogen. Now both of the electrons are being given by the nitrogen atom. That's how you form that structure. Okay, let's talk about the VB theory. Now, hopefully you have consolidated the basic principles, how to draw the Lewis structure through the Lewis theory. The idea there was that you want to have a complete octet for as many elements as possible, and a duet for elements such as hydrogen, helium, lithium, and beryllium, because they are closer to helium and it has only 2 electrons in the system. Also realize that Lewis structures basically just give you an idea on the connectivity. It has absolutely no connection to the shape of the molecule. You know nothing about the physical properties of the molecules. All you get is the connectivity because you want to maintain that octet, and that's it. I would also want to say here, you don't get any information on the kind of orbitals that will overlap with each other in a Lewis theory. So Lewis theory basically gives you a two-dimensional representation in black and white what the molecule is going to look like in terms of what's bonded to what, and that's it. Now, valence bond theory is a more advanced theory which gives you information as to how the bonds are being formed. And one of the postulates for valence bond method is that a covalent bond, when that gets formed, it essentially gets formed by the overlap of atomic orbitals. And the combining orbitals must have electrons of opposite spin. And essentially, it's the extent of the overlap which basically gives you information about the strength of a bond. What do I mean by that? Well, let's say it's an s orbital, and it's an s orbital, it's spherical, and there's another s orbital, which is also spherical. And I'm giving you, you know, I'm giving you just a pictorial representation to, let's say one of them is a big one and the other one is really tiny. Okay, so the extent of overlap is right over here, this part. And since it's little, essentially you can call this a weak bond. Now envision that you have one, and now the extent of overlap is larger, and that means that this will be a strong bond. Okay, so each of the bonded atoms, they are going to maintain their own orbitals, but the electron pair which is present in the bond is going to be shared. So that means that each of the atoms is going to have a say in that electron density. Of course, you know that electronegative elements, they have a greater affinity towards electrons, so they would like to pull the electrons towards themselves a little bit more. But even so, both of those combining elements will contribute towards that electron density. Now, recall in General Chemistry 1, we talked about a concept of hybrid atomic orbitals or hybridization. Hybridization. In other words, sp3, sp2, sp, sp3d2, etc. That's what we discussed. When an sp3 orbital is formed, it's one s orbital combining with three p orbitals. Now, there are certain rules that we have to follow for hybridization. If one s is combining with 3, that means there's a total of 1, 1, 2, 3. So total of 1, 2, 3, 4 orbitals. So if 4 orbitals are combining, then it has to give rise to 4 hybrid orbitals as well. That means the number of orbitals combining in and the number of orbitals that are formed is the same. Okay. Now, consider the case of perhaps methane, CH4. Now, when you have to draw the Lewis structure, and that really is the first step of determining, and in this case, I'm going to go over the whole process just to kind of, get you started. But I am going to give you a shortcut method to get this again from the perspective of the exams, how you can answer that real quick. When you draw the Lewis structure, this is the Lewis structure for methane. So you see that there are 4 single bonds. 4 single bonds. So these are all sigma bonds. Single bonds are sigma bonds. Sigma bonds. So you would say, well, carbon, if somebody asks you which orbital on carbon is participating in bonding, you'll be like, well, the valence orbitals, right? So the configuration of carbon is going to be, since atomic number is 6, it's going to be 1s2, 2s2, 2p2. So when you look at the valence shell, looks like it's going to contain 2 electrons in the 2p orbital. But I want to form 4 bonds. How can I accomplish that? And one way to do so would be that one of the electrons from the 2s is going to get excited up to and get promoted to the 2p. And the reason why that's happening is because when the hybridization, which basically would mean that you are going to redistribute the energy energetically, it's a more favored process. So you're going to end up with 4 hybrid orbitals, each containing 1 electron. Now, when you have 4 orbitals, it takes up the shape of a tetrahedron. So your hybridized carbon atom is going to point towards the corners of a tetrahedron. Look at the pyramid type structure, right? Didn't come out exactly as I expected it to, but approximately. And the corners of those will be taken up by hydrogen. 1 electron is coming from each of the 2 atoms, carbon and hydrogen, and that's how you get the single bond. Now, if somebody asks you which orbitals are participating in this, because it's a combination of the s and 3 p's, in other words, an sp3, you would say sp3 hybridized orbital on carbon overlaps with s orbital on hydrogen. Realize that the 1s on hydrogen cannot hybridize with anything because there is only 1 electron, there is only 1 orbital. What is it going to hybridize with? There is no room essentially in case of hydrogen. So the hydrogen is going to be only the 1s, but on carbon you do have the sp3 orbital. Now, physically, what does this mean? Because really hybridization is a very abstract concept. But what does it actually mean? Consider a situation if you have a room, okay, you have a room which has 4 walls, and you're given 4 buckets of paint. 4 buckets of paint. One is, let's say, blue, and there are 3 that are red. That's a pretty fantastic room there. But let's say you have 1 blue and 3 red, okay? And you're also told that each bucket, so 1 bucket per wall is what you will need. There are 2 ways to paint this. One would be that you paint this with 3 walls. So you can have either three red walls and 1 blue accent wall, or if you believe in things being uniform, what would you do? You would pitch in the paint, so you would get 4 buckets of purple-ish color, and you're going to paint all 4 into 1 uniform purple color. And that is the concept of hybridization. That what we do is we pitch in the electron density and we redistribute that into the 4 hybrid orbitals. That's exactly what we do. So just like we mixed the 1 blue with the 3 red to get a purple color, and then we redistributed it back to the 4 buckets so that each bucket to each wall, that rule is still followed. That's exactly what we do in case of hybridization. We bring in all the energy, all the electron density together, and then we redistribute in order to get our electron density in the hybrid orbitals now. And in doing so, depending on the molecule, we can have an sp hybrid orbital, such as in the case of acetylene, 1s and 1p. That means you have 2 hybrid orbitals that are coming in, and that would mean that 1s would have combined with 1p, and this would be what you would do when your requirement was only 2 orbitals. That's when you would do something like this. And how would I know that my requirement is 2? I want you to look at the Lewis structure. This is the Lewis structure of acetylene. You have a triple bond between the 2 carbon atoms and a single bond with each of the hydrogens. What does that tell you in terms of steric number or VSEPR model? It tells you that there is 1 electron group over here and another electron group over here for this carbon. Likewise, if you look at the other carbon, you have an electronic group on the left side, you have an electron group on the right side. So you need only 2 orbitals, and hence you mix the S and the P with a possibility to get only 2 hybrid orbitals. So one S and one P orbital put together is going to give you your sp hybrid orbital. sp hybrid orbital. Now, in terms of the bond angle is going to be 180 degrees, and the shape for this kind of a structure is going to be a linear structure. If you compare that of hybridization, which is sp2, so what would sp2 mean? sp2 would mean you have mixed one s and 2 p orbitals, and that would mean you have a total of 1 plus 2, total of 3. So your requirement should be for 3. So let's see if you actually have that. You have to form one CH bond, you have to form another CH bond over here, and then there is a double bond. So this is going to take the shape of a trigonal planar. The bond angle is going to be 120 degrees, and if the steric number is 3, this is what you're going to do. You're going to mix the 1s with the 2p. So long story short, what you need to do is anytime you are given a structure, get the Lewis, or a formula, get the Lewis structure, count the steric number or electron group around the central atom, and then decide whether it's sp3, sp, or sp2. If you need 3 orbitals, that would mean you're seeking an sp2 type of a hybridization for a carbon. If you need only 2, that would mean that you're seeking an sp type of a hybridization, and when it is 4, you say it is sp3. So there are 3 kinds. Because my hero is carbon, there's only 3 kinds of hybridization you need to worry about. Notice 1 plus 1 is 2, 1 plus 2 is 3, and 1 plus 3 is 4. So when your requirement for the hybrid orbitals is 2, you would say it is sp hybridization. When the requirement is 3, you say it's sp2. When the requirement is 4, you say it's sp3. A quicker way, less than 5-second rule, would be when there is a triple bond, it is sp hybridized. When there is a double bond on carbon, it's sp2. And when there is a single bond, it will be sp3. So 3, 2, and 1, and 1, 2, and 3. And so 3 plus 1 is still 4, 2 plus 2 is still 4, 1 plus 3 is also 4, because carbon can form. You got it. Total 4 bonds. All right. Likewise, if you're thinking about pi system, a pi bond is essentially a bond which is not a head-on overlap but sideways overlap. So that's a pi orbitals or a p orbital, and this is a p orbital. It forms an overlap here and an overlap here. So realize that a pi bond can touch at 2 spots. However, this touch is sideways, it's lateral overlap, it's not head-on overlap. And so the overlap is not to the same extent as a sigma bond. So pi bond by itself is weak. However, pi bond cannot sustain. It's so weak that it cannot sustain itself. So you will never have a pi bond alone. You always will have a pi bond in conjunction to a sigma bond. That means only if a first preliminary sigma bond has formed can you seek a pi bond. What do I mean by that? Let's say you have the molecule of ethene, which we are saying is sp2 hybridized. Now, each of these single bonds, these are sigma bonds. sigma, sigma. And they have been formed between the sp2 on carbon and the s orbital on hydrogen. That's how we got them. One of these is a single bond which will be formed between sp2 on this carbon and sp2 on the other carbon. But the other is going to be a pi. So notice that a pi cannot, I did not label any of the CHs as a pi bond. I labeled those as sigma. So the first bond that gets formed between any two atoms is a sigma bond. It has to be. And any additional would be a pi bond. So a pi bond is nothing but a p orbital overlap. And it's a sideways overlap. So since it's present in conjunction to the sigma, of course you can say that the sigma and pi, which basically is a double bond, is going to be stronger than a sigma bond alone, which is a single bond. Likewise, you will say that 1 sigma plus 2 pi bonds, which is a triple bond, is going to be stronger than a double bond. You know that from Gen Chem 1. But a pi bond by itself, if you're saying, that's not going to be as strong because it's only a sideways overlap. And here I'm showing you sp3 hybridized ethane molecule. So notice the s combining with the 3 p orbitals to generate 4 sp3 hybrid orbitals. So if somebody says when one s combines with 3 2p orbitals, how many hybrid orbitals are generated? You always, since you combine one s with 3p, it's going to give you total of 4 orbitals. And notice each of these bonds is going to be a single bond, and all of these are single bonds and also the sigma bonds. The bond angle in this case is going to be 109.5 degrees, and the geometry is going to be tetrahedral. Now, depending on whether it's ammonia or water, it could be a distorted tetrahedral, and that's a different story about the lone pair repulsion that will be present in those kind of molecules. So what that means is that if you have ammonia, for instance, NH3, the Lewis structure suggests 1 electron group, 2 electron group, 3 electron, and 4 electron group. So the nitrogen in this case would also be sp3. But since there is a lone pair that is present over here, it's going to repel the bonded electron pairs. And so the bond angle between the two, the H and H bond system, that is going to be less than 109.5, and it actually has been found to be 107 because of the presence of the lone pair, which takes up the space in the molecule. Okay, let's see if we can apply what we heard. Let's see if we can apply that to the slide. The question is, what is the hybridization of the non-hydrogen atoms? And we are seeking non-hydrogen because hydrogen only has one s, so that doesn't go any hybridization there. So each of these locations, consider that to be a carbon. So all you have to see is whether carbon has a double bond, single bond, or what. So since carbon has a single bond, this will be sp3. This will be sp3 again. This is a double bond, so that will be sp2. This is also a double bond, so that too will be sp2. Likewise, the second one, sp3, 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 that's a double bond right there. So that will be sp2. Consider oxygens. In this case, oxygen is forming a double bond, so that will also be sp2. Oxygen here is forming single bonds. The total number of stereo groups is 4 around oxygen, so that will be sp3. Notice item number 3. Both of the carbons are sp3, and oxygen also is surrounded by 4 electron groups, so that too is sp3. In the last case, you have triple bond, and so each of those is sp hybridized structure. Okay, so the last thing that I would go over is the various different kind of formulas that we will be seeing, and there are some that we are going to follow throughout Organic 1 and Organic 2. So let's connect from what we already know. This molecule that we are going to refer to is acetic acid, and you know that from General Chemistry 1, when you did vinegar, which is a 5% solution of acetic acid in water. The formula for that is, molecular formula for that is C2H4O2. So a lot of times your book will also give you the corresponding anion as C2H3O2 with a negative sign. And then of course in the General Chemistry 2, you were given the phase to acetic acid, which is CH3. Let's maybe change the color. CH3COOH. In that sense, you refer to acetate as CH3COO with a negative sign. So now, of course, you're seeing where the bonding is. Recall what you learned in Gen Chem 1. There's a concept of what is called as empirical formula or simple formula, which basically looks at the ratio of the various different elements that are present in a certain compound. So for example, if you're looking at C2H4O2, you have 2 of the carbon, 4 of the hydrogen, and 2 of oxygen again. So all 3 are divisible by 2. You can have a simple ratio as CH2O. And so CH2O is your empirical formula. On the other hand, C2H4O2 is your molecular formula. Realize that empirical formula only gives you the ratio of the atoms that are present. On the other hand, molecular formula gives you the exact number of atoms of a certain element. So in that sense, there could be 2 different compounds which have the same empirical formula, but either of the 2 do not give you any information about the structure of the compound. For that, you need to write the Lewis structure of the compound so that you can look at the connectivity and make a connection of which atoms are connected to which other atoms. Now, if you look at the condensed structural formula, that's what's going on here. So you're writing that as CH3COOH, and in that sense you have the connection that there is a CH3, which is also referred to as the methyl group, as we will learn in chapter 3, which is then connected to a carbon, and then we have 2 oxygens followed by hydrogen. But the complete idea is provided by what is called as the structural formula or the full structural formula, in which you are actually showing where are the double bonds, where are the single bonds, and what is connected to what. So essentially, in a full structural formula, you're writing that as a Kekulé structure without the lone pair of electrons, but you are making connections with where your double or triple bonds are and where the single bonds are. We are going to follow what is referred to as the line angle or the skeletal formula. And so it's to your benefit if you start using this at an early stage. Let's take a look how line angle or skeletal formula is different from the structural formula. In case of a line angle formula, every connection or every point of intersection between lines is a carbon atom. These are written in a manner such that the double bond, which will have an sp2 hybridization, is going to be shown, ballpark. I'm not going to sit there with a protractor to measure the angle, but you will see that ballpark, it is going to be about 120 degrees. So as you can see, in this particular case, the C double bond OOH. Now I'm writing the oxygen in this case because that is neither carbon nor hydrogen. So anything other than carbon or hydrogen will have to be shown. All the hydrogens that are connected to these heteroatoms will have to be shown as well because they define your functionality. This is where the functionality is. Functionality. And again, the point of intersection is going to be your carbon atom. Likewise, if you have a carbon which is terminating to nothing, so there is no further chain, that automatically means that that is a free methyl group. So that's a CH3. And that is the reason the peripheral CH3 is shown ending like that. So let's take a look at some other I'm referring to. Let's say I said point of intersection. So this is a line, this is a line, and the point of intersection is right over here. So there should be a carbon. Likewise, there will be a carbon here. This also means a carbon. This is a carbon which is connected to two other carbon units. That means the other two must be hydrogens. What is not shown is a hydrogen. Likewise, this should be two hydrogens as well. The two remaining bonds should be hydrogens as well. The two terminal ones, and I'm going to put those in a square so you can differentiate between the two. They're connected to only one other carbon atom, maybe like that. And so the remaining three bonds now are going to go to hydrogen. Since you're just getting started, if I were you, I would write down the line angle skeletal while you're practicing. But also at the same time as you're drawing the resonance structures and stuff, it's a good idea to perhaps show the hydrogen atoms for yourself on the side and kind of compare and contrast to be able to see that you actually have gotten the correct structure. So the expanded structure of this will be 1, 2, 3, 4, and 5. So that's 2, 3, 4, and 5. And let me also 3, 4, and 5. And let me also connect all the bonds. Notice these two terminal ones are connected to hydrogens. So now if you're writing it in the full structural format, you will have to take the time to show all the hydrogens. And the only reason I have color coded the three are because these three are CH2s, also referred to as methylene group, whereas the ones that are terminal, peripheral, outer, whichever word you want to use, those are CH3s, and those are referred to as methyl groups. And if you wanted to convert that into a line angle skeletal, since it contains 5 carbons, you would just say it's 1, 2, 3, 4, and 5. That's it. And if you wanted to convert that to a condensed structure, there are some various different ways that you can do that. You can condense all the like groups together. So that's a CH3. But I'm going to write it as H3C because it's connected to a carbon. And then we have a CH2, and then another CH2, and then a CH2, and the last one is CH3 again. Notice these three are exactly the same, so I can even write this as H3C, CH2, whole thrice, and then CH3. So when you count, you would say 3 carbons from the CH2s, 4th carbon, and 5th carbon. Still contains 5 carbons. Nomenclature aspect of it, we will talk about that in chapter 3 in really good detail. But for now, you should understand, you should realize that expanded structure, condensed form, or line angle, 3 different ways to draw the same thing, and they basically give us the connectivity, the information as to what's connected to what. Either way, if you have a heteroatom, that must be shown, any hydrogen that is connected to that heteroatom must be shown as well, because these heteroatoms are usually parts of the functionality, and it's a good idea to be as clear as possible in that functionality. Now let's talk about the next thing. So over here I'm showing you 2-butene, which contains 4 carbons, 3 and 4. Notice the double bond is between carbon number 2 and carbon number 3, and there's two ways to really represent that. In the first case, hopefully you have identified that this is a full structural formula. The reason why I'm calling it a full structural formula again is because I have expanded. I am actually showing every single bond that is present in the molecule. If I have to draw the condensed form, so these are all condensed structures, I'm going to condense this part into the methyl. I'm going to condense the CH and then another CH and then a CH3. Now the fact that it is a CH and a CH automatically would mean that there is a double bond that is present in between. Or you can show the double bond to explicitly say that it is an alkane. Again, notice in case of acetonitrile, acetaldehyde, acetone, acetic acid, we have shown all the heteroatoms completely. On the other hand, when we are referring to the condensed structures, will not show the methyl parts written down completely. We will refer to it only as a CH3. Likewise, if you notice here I have the condensed structures and I'm converting that into the line angle skeletal. And so in this case I have 4 carbons from the CH2, fifth and the sixth carbon. So those are 6 carbons, 1, 2, 3, 4, 5, and 6. 2, 3, 4, 5, and 6. Likewise, notice the second one has 6 carbons again, but there is a double bond between carbon number 2 and carbon number 3, and that's what I'm showing you here. So a good strategy in going from one structure to another is that you should number your carbons. A, you're not going to miss the number of carbons, and B, if there is a functionality such as a double bond or an actual functionality, you would be able to exactly provide the position, the location on your structure. Another thing that I would like to mention here is the use of parentheses. Anytime you see something in parentheses, that basically means that that particular group or substituent, when I use the word substituent, it means like a CH3, that is falling off of the carbon preceding that. So what that means is 1, 2, 3, 4, 5, 6. Your chain contains 6 carbon atoms, and the OH, which is in the parentheses, is going to fall off the third position as a pendant, just like that, as if 1 through 6 was a necklace and the pendant is at position number 3. So hopefully you can visualize and interconvert between the two. All right, the question here is draw the condensed structural formula for the following. So first things first, you should take the time to number these. It contains 7. So there's 2 ways to really do that. You could either say that it's CH3, CH2, 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 CH2. That makes 5, 6, and 7. So that's one possibility. Or you could just say it's CH3 and then 5 CH2s are locked in between, and so that makes 7 as well. That's one possibility. This is acetone, so if this is ending in just one carbon, that means you can write it as CH3C, OCH3, or you can write it as COCH3 as well. Both of those are acceptable. In this case, you should start from here because 1, 2, and 3, those 3 are all similar groups. So 1, 2, 3, and then these 2 can be treated similar. So you will say it's carbon on which you have 3 different methyls, and then there is a CH2, and then there is another carbon on which you have a hydrogen, because this was going to be hydrogen, and then 2 methyl groups. That's one way. Some people would say they would want to include, so they would say that it's a 5-member chain, so they would write it as CH3, C, CH3 with 2 methyls, CH2, which is right over here, CH with 1 methyl, and then a CH3. I don't quite completely agree with that particular one because these 2 methyls are exactly the same. Why not consolidate that? Likewise, if these 2 methyls are exactly the same as the third methyl, why not consolidate that? So I would go with the one in blue rather than the one in the red. 4 is going to be 1, 2, 3, 4. So it's a chain that contains 4 carbons. When you don't see the bond, you can perhaps write down the hydrogen. The pendant now pointing upwards, it should be in parentheses, CH2 and CH3. That's what you should get. Okay, the next question is draw the skeletal structure. So you're given total 4, 5, and 6. So you would say 6, 1, 2, 3, 4, 5, and 6. Next one is CH3, CH3 twice. So this is again similar to what we were discussing just a couple minutes ago. On that carbon, so let's number 1, 2, this is 2, this is 1, and 2 methyls are on carbon number 2. Let's take a look at 3, 1, on the carbon you have a methyl, and then you have another carbon, so 1, 2, 3, 4, and 5. Notice everything that's in parentheses, I did not number that. So your chain is 1, 2, 3, 4, and 5, 4, and 5. And on 3, you have an ethyl group. You really could have written, this really could have, should have been written as CH, CH3 twice, CH, CH2, CH3 whole twice. That would be okay. And then you have CCH3 4, which would mean you have a carbon in the middle, and then it's connected to 4 methyls on all directions. So that's going to be your item number 4. The next question is, carbon responsible for the odor of spearmint has the following structure. How many hydrogens are bonded to each carbon? Provide the molecular formula of carbon. So these are 2 structures. I gave you that earlier as well. You're just supposed to provide what the molecular formula is. So this really is your ability to be able to count once you have figured out what is each group. Notice we have carbon, hydrogen, and oxygen. Whenever there is a group that terminates into nothing, that means this is a CH3. Point of intersections, those are all carbon atoms. So these are all carbon atoms. This is a carbon, this is a carbon, this is a carbon. Again, when it points to nothing, that will be a CH3. When it points to here, 2 bonds, that means the other 2 are going to a hydrogen. Again, in this case, all 4 are going to carbon atoms. This carbon atom is bonded in 3 directions. That means there is 1 hydrogen here. This is bonded to 1 carbon and another carbon. That means it's a CH2. This one contains a hydrogen, carbon, carbon, and carbon on each side. This should be a CH2. We don't have anything there because the valency is saturated. So there's only 1 oxygen. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And now likewise, if you count the number of hydrogen atoms, that'll come out to be 14. So your molecular formula should be C10H14O. Okay, this is it for chapter 1. You should work on the problem set, explain your work as much as possible, and we'll go over chapter 2 now.